I forgot to suggest at the end of the last screencast to do homework 1, problem 5. If you haven't done it, it would be a good idea. This screencast is about checking the model assumptions. The result we considered earlier that said MSA over MSW had an FC-1 N-C probability distribution is conditioned on the model assumptions being true. Before we can rely on the p-value, which is computed based on MSA over MSW having a FC-1 N-C probability distribution, we need to verify that the model assumptions hold in our example. Recall that the model assumptions are: the samples are independent of each other and each sample was obtained randomly. Each sample is taken from a normal population and the normal populations have equal variances. We'll go through each model assumption one at a time. The first assumption is sampling is independent and random. There isn't a way, after the study is complete, to go back and determine whether the correct sampling methodology was applied. If we weren't part of the study, we have to decide whether we trust that those doing it followed the correct data collection procedures. As an academic exercise, we'll believe that this model assumption is correct. The second model assumption is sampling is from a normal population. We'll use a scatter plot of the data to evaluate this and to evaluate the next model assumption. The scatter plot is repeated at the top of the next page. Here's the sample 1 data. Could these observations have come from a normal distribution? Could the sample 2 data observations have come from a normal distribution? Does the data tend to bunch in the middle? Does it distribute more or less evenly? Before we make a final decision on this, remembering there's only 5 data points, let's look at this confidence result. The result says if the other model assumptions hold, the conclusion that MSA over MSW has the appropriate F distribution is quite robust to the assumption that the individual populations are normally distributed. What that says is, even if a population is only approximately normally distributed, MSA over MSW still has approximately the correct F distribution. That is, unless the data shows major gaps, and this really isn't major, or a definite lack of symmetry, it's okay to assume that the data has been obtained from a normal, at least an approximately normal distribution. Given this scatter plot, we'll assume the normality assumption is verified. The third and final model assumption we have to check is the equal variance assumption. Remember that a standard deviation is simply the square root of a variance, so to say equal variance is the same as to say equal standard deviation. Sometimes the equal variance assumption is referred to as the homoscedasticity assumption. If we computed the variance or standard deviation for this sample, would we get about the same value as if we computed the variance or standard deviation for this sample? I guess just looking at these pictures, we'd have to agree that, yeah, we probably get very close to the same answers. But we even have a confidence result for the equal variance assumption. It basically says, even if the sample variances are approximately equal, the probability distribution for MSA over MSW remains very close to the appropriate F distribution. Again, we can be fairly liberal in assuming the equal variance assumption is satisfied. Sometimes in closer calls, this conservative working rule on equal population variances is useful. It says, if the largest sample standard deviation does not exceed approximately the square root of C plus 2 times the smallest sample standard deviation, then the population variances can be considered equal. Remember, C simply refers to the number of populations or the number of samples. They're the same that we're working with. In this case, we have only 2 stores that we're working with, so a C plus 2 is 2 plus 2, or 4. Square root of 4 is 2. In other cases, this number will be slightly larger. I'll ask you to use the working rule in homework. Even though we don't need it in our 2-store example, let's apply it anyhow for practice. To compute the sample 1 variation, we simply take each observation, subtract off the sample 1 mean for all 5 of the observations, and you might remember when you compute a sample variance, you divide by n minus 1, in this case 5 minus 1, which comes out to be 103. To get the sample 1 standard deviation, you take the square root of the variance, in this case 10.15. There's a text box here, of course, that you can pull down, but I'm going to let you, for practice, compute the sample 2 variance, take its square root, and get the sample 2 standard deviation, and then determine whether the largest of these 2 standard deviations is less than twice the smallest. If the largest is less than twice the smallest, then it's okay to assume that the population variances are the same. The last screencast will be about actually using Excel to obtain a scatter plot. After you complete the final screencast, would be a good time to do homework 1, problem number 6. Here is a quick summary of the solution process that you go through in doing a one-way analysis of variance problem. And here's a few examples of other places where one-way analysis of variance might apply. There are many more.